Welcome to the video. We are going to solve gray to binary equivalent. So this question is very easy but confusing. I will tell you how it does. So in this question you are given, we'll see with example. You are given a number, integer number, decimal number, okay? And you have to first convert that number into gray code, okay? So with the given chart, since the number is 4, see for decimal number 4, what is the gray code? It is 1 1 and 0. 1 1 and 0. Now you have to find its binary equivalent of this gray code. Now for 4, gray code is 110. However, the binary code is 100, which is 100. 100. Cool. And now again you have to find what is 100 in gray code. So you have to find, is there 100 in gray code? Yes, it is here. 100 in gray code is here. And now what is its decimal number? Decimal equivalent, it is 7. So this is what you have to do. See example 2. The number is 15. Number is 15. Number is 15. And now the gray code representation of 15 is 1000. 1000. 1000 is the gray code representation of number, decimal number 15. And if you'll build a table, you'll see, I'm not going to build a table, but I will tell you what gray code is. So first of all, gray code is similar to this extended version of binary numbers, gray numbers. So it the difference is that rather than doing the operations with the two, we see that there are we do factorization with two. Now we will see for the initial number. See the chart. It starts from 000. For the next number you have to move, you will only change one bit. And not touch any other thing. So from 000 you got 001. Then you again changed one bit, you got 011. Then you again changed only one bit and got 010. Then again you just toggled the one bit and you got 110, then 111, then 101. So for a number n, if you have to go from n to n plus 1, you will only toggle one bit of the previous number n. Okay, so gray code representation of 15, decimal 15 is 1000. And similarly, gray code binary representation for 1000 will be 1111, 1111. If you can see 15, 8, 4, 2, 1, 8, 4, 12, 12 to 14, 14, 1, 15, 15. Okay, 15. And now you have to return the what 1111 stands at in the gray code representation. In gray code representation, 1111 is 10. So first of all thing is, you have a number. Let's say you have given number n. Okay, you have a given number. You have to convert it into binary number. Convert this number n to binary, and then convert. You have to find that binary gray code equivalent of that number. So how we will do it? Okay. So first of all, I will convert the gray code number n to binary. Okay. Gray code. We are given the number in gray code format. Okay. The decimal number, but that decimal number is for gray code, not for binary code. Okay. So first of all, I'll create a variable, binary variable, and I will store the binary representation of this number. Binary representation of the number, but it starts from 2. Why? Because if you convert an integer to binary in Python, it will add prefix 0b, 0b in the beginning, 0b in the beginning. Okay, so we have to just omit it so that we get the exact binary number. Okay, then I will create result variable that will store the first digit of this number. Why? So this result is initialized with the first bit of the binary representation, which is denoted by binary 0. Okay, now we got the first bit. Now we will iterate through the remaining bits of binary representation, which is from binary 1 to the very end. Okay, using a for loop we will do that. So for I in range, we got 0th bit. We'll take the first bit now, start from bit 1, and we'll go till length of binary, all the elements which are there, all the numbers which are there in the binary. Okay, now for each iteration, we will perform a XOR operation. XOR operation between what? The previous number in its the integer format, integer representation of the previous number which you have calculated, and the last number, not previous, the last number which you have calculated, and between the current binary representation number. I will do it. So we will and append it to the same in the calculated result, and we have to do in string since it is a binary. So first integer representation of the result, last character. That is what we do. We have to change only one bit. We have to change only one bit, and we will do in the what? We'll do in the end. Okay, from the left rightmost side. Okay, that is why we took the rightmost character minus one, which is last rightmost character of the result which you have formed. We will do a XOR operation between this and the integer representation of this binary I character of binary. Integer representation of, so integer is formally right. We have to do XOR operation. We have to do in integer because otherwise it will be in string format. So what we did, we are doing XOR with the last character of result, the number, the gray code number, last character, and we'll do XOR with the its binary ith character of binary representation, ith character of binary representation, because in gray code we only toggle one bit. Okay, we only toggle one bit, and we'll do from the end. At the end, we'll return the number result, but we have to return in the integer format. That is why we'll convert it into integer format, typecast into integer format, and we'll return it. Let us submit and check the efficacy of our solution. Yeah, it does the job pretty effortlessly and in very less time. So I will again reiterate, you have to study about what gray code is. So gray code is nothing. So extended version of binary numbers, with a difference that rather than factorizing it with 2, we only alter the one bit from the rightmost side to move to the next number. So I hope you learned it and enjoyed it. Thank you. Have a very nice day.